Hello students, welcome to Saraswat classes. I'm your educator for solution of chemistry section C, inorganic and organic part for the NET CSIR exam. Okay, held on 13th November. Now the question was, the sequence through which the following reaction proceed is, we have to choose from these options. Now here we have a quinonide molecule, and it is derivatized with a allylic group. Basically, it is an allylic ether. And as you can see in the ortho position, here there is a methyl group, so it is locked in the ortho position. Now, if you're going to heat such a compound, then what happens over here is, as you can see in the mechanism, that it will undergo a 3,3 sigma tropic shift, okay? And this will undergo rearrangement. But since the ortho position is blocked, so here the group will come to the para position where there is a nitrogen, okay? So we will call this as a para-Claisen rearrangement, all right? When I say 3,3, what I mean is I will take oxygen as number 1, this as number 2, and this as number 3, whereas this particular carbon will be called as 1', 2', and 3'. Okay, just to make you understand the movement of the carbon and the connectivity, I have put an asterisk sign over here. So when there is a first 3,3 rearrangement, this carbon will join over here, and the movement of electron will be like this, as shown in the arrow. This bond will break, so there will be C double bond O, and this pi bond will come over here, okay, and this particular carbon will join over here. So if we do the rearrangement, we get this kind of a molecule. All right. Now, again, there will be another Claisen 3,3 sigma tropic shift, eventually giving you the para-Claisen rearrangement product. So here we will again consider this to be as 1, 2, and 3, and this as 1, 2, and 3. So this carbon will now join with this nitrogen, okay? And after the 3,3 sigma tropic shift, our product will be looking something like this. Okay. Now, there will be an enolization over here, tautomerization over here. So what will happen, this particular proton will be lost, and there's a proton movement from here to this oxygen. So there is a double bond over here, and then we can think this particular pi electron cloud over here going, and the O, C double bond O will open up, and so we get a minus charge over here that will be protonated then. So this will be our compound, as you can see over here now. All right. Okay. Now this particular compound will undergo a Cope type of rearrangement. In which we'll consider again this to be 1, 2, and 3, and from here this is going to be 1', 2', and 3'. So effectively this bond will break. Okay, so this cloud will go here, that cloud goes here, okay, and that comes over here. Now this bond will break, and there will be a pi bond here. Okay, there will be a sigma CC bond over here, and this pi electron cloud will go here. If we do that, we get this molecule over here now. So we are seeing that in the initial step, there is a Claisen rearrangement, okay, and that is twice, all right, and then followed by tautomerism, and then we have a Cope rearrangement. So looking at the options and following the sequence of the reaction, we can say 1 should be our correct answer over here. In the next question, that is question number 85. Here, okay, this is no group, okay, just there is no line over here basically. So this particular carbon is having a methyl group over here, and we have been given Me2Cu Li, okay, in presence of ether, and the temperature is -78 degree. So under this condition, basically this is a Gilman reaction where when methyl groups are attached to copper and they have to undergo a reaction with the alpha beta unsaturated ketone, instead of making a 1-2 attacks, if you take this one as 1, this is 2, okay. Here, because it is attached to copper and not to magnesium, all right, so here the attack will take place in the 4th position. So this is undergoing a 1,4 addition reaction. One can remember that Gilman reagents, they undergo 1,4 reaction with alpha beta unsaturated ketones or aldehydes. To understand the stereochemistry of the reaction, what we will do is we will write this particular ketone in a chair form. And once we do that, the information that comes clear to us that if the methyl is going to approach from this side, then there is 2 hydrogen which will be giving it a diaxial interaction, 1,3 type of diaxial interaction, okay. And if it is approaching from here, then there is no such interaction, okay. There is rather only 1 hydrogen to give you that interaction. So preferably the methyl will now come from rather the hydrogen should have been here, okay, not this one, but here there will be hydrogen. So the methyl will come from here. It is going to face more repulsion, and the methyl will come from the top. So there will be a movement of electron cloud from here to here, and the C double bond O will open up, and the molecule that we will get will be having a structure something like this, which is basically a enolate. Now this enolate will make a nucleophilic attack on the alpha beta unsaturated ketone. Rather, you can say it is going a Michael type of addition, which is 1,4 addition again. And after we do the reaction, so once this is attacking over here, the double bond comes here, this becomes C double bond O becomes CO minus. So we get this molecule. Now we protonate this O minus using water, because water is there now in the medium. Okay, and so it will get an enol, which will tautomerize to give you this kind of a ketone. Now, thing to notice over here is that there is a alpha CH over here and there is alpha CH over here. So under conditions where this is basic, protons can be taken up from here and also here. But if you make an attack from here, it is forming a 4-membered ring, which will be sterically or it will be much more strained, I should say. Whereas if you make an attack from here, then the beta hydroxy alcohol that will be formed on this attack, okay, that will be a 6-membered ring, where if you make an attack from here, it will be a 4-membered ring. As I said, 4-membered rings are more strained than 6-membered rings. So it is better to say that the 6-membered ring will be the preferred product, okay. So what happens now, this will make an attack here under the reaction conditions where there is heat, water will be lost, okay. So you can simply think this carbon that is there, 2 hydrogens from here and the oxygen from here will be removed. You just take out water and there is a double bond, all right. Now, over from this stage of the reaction, you can remove 2 and 3 as the option, because as you can see over here, both the methyl groups are going to be on the same side. Here it is in the axial position, there is in the equatorial position. So they are both in the same side. So we will look for methyls which are in the same side. Here this is in the same side and here. So this and this 2 and 3 are not the correct option. We have to exclude 1 using the reason that 4-membered unsaturated, okay, rings are more strained, so it will not be formed. But 6-membered unsaturated rings are comparatively more stable, so they will be formed. And this last step is basically intramolecular hydrogen condensation reaction. So having gone through all these reasons, we can say that 4 is our answer now over here. Okay, for the next one, Here in the question 87, we have to find out the product that is formed. Okay. And here, if you're treating with thionyl chloride, acid becomes converted to acid chloride. Okay. And then we have a diazomethane, so which will be making an attack to the carbonyl group, and a nucleophilic substitution addition reaction will take place to form a diazoketone. Okay. Now, the diazoketone, if you give it light, it undergoes a cleavage where the nitrogen is going to be removed, and it leads to the formation of a ketocarbene. And this kind of ketocarbons can undergo rearrangement. So here this group bond will break, and this total group will transfer over this carbon, and consequently this will create a double bond over here. So this is breaking, it generates a positive charge. So this joins here, and then this is making a double bond. So we get a ketene type of a system, all right. Now, what happens next is, for this ketene type of system, we can think, since there is no water or acid or any other ammonia, such type of things, so what will happen here, the ketene, we can think, will undergo the attack from the pi electron over here. And so we can think of a ring formation. So if this is attacking here, then the C double bond O will break up. Okay, formation of a minus charge here. The C double bond is intact. Okay, and the attack will take place in such a way that the most stable carbocation is formed. Okay, so if there's a possibility of plus charge here and here, then this is where the plus charge will be generated. So this carbon will be joined to here. Okay, and now in the next step, if you bring back the C double bond O by making a double bond over here, then this pi electron will open up, and that will now join to this carbon over here. So if you number this molecule, looking at all the options, I'm choosing this molecule because this is the one that is the correct answer. If you number this molecule, then this is your carbon. Okay, next to it, this is 2. So 2 is joined to 7, as you can see. All right, and C is also joined to 6, as you can see over here. So this 1, 2, okay, 7 and 6 is the 4-membered ring that is over here. All right, and just check out the rest of the numberings, which is going to fit the answer 4. So this is how this reaction is taking place. Okay, so I hope that clarifies the questions that you had made, and keep visiting Sarosar classes, okay, for more solutions. And I hope you have liked the kind of explanation we have given over here. And thanks for listening. Have a great day.